All right, welcome everybody to a brand new day of computer science. Today we are going to be working together to build some sort of like pool simulator or something like that. So as you can see, we've got a ball on a pool table and it's bouncing around and hitting the different edges. And there's rounding, it's rounding, but like basically you can see this Dragon Ball here is bouncing off the different walls. And when it hits one edge, then it goes the other way and things like that. So it bounces up, things like that. It rounds to the nearest row, so you can see it like kind of like going inside of the wall there and stuff like that. But you get the idea. Okay, so whenever we work on a project like this, it's really useful to start by just kind of like sketching out your idea. A lot of students at this point in their career are just kind of like, all right, I kind of get things, but I don't really get them. You know what I mean? Like I could do like a function. It's like the DVD video. Exactly. There's a great scene in The Office like that where people are like watching the DVD logo bounce around. But students are like, okay, I kind of get it. Like I can kind of probably figure out how to do something like that, but they don't really have a systematic approach to taking it. So what I'm going to show you guys today is sort of my systematic approach for building like a billiards game or something like that. And then together we'll code up basically something along those lines by the end of class today. So a little presentation here for you. And how many rows do you think the TV logo has? Okay, so this is what I call coding from concept. I don't know if this is a real term, but it's my term at least. And so you have a concept for something in your head, like for a pool game or something like that. Now we've only got one ball in that simulation, but that's a good starting point. Okay, so yeah, so one of the biggest problems in programming is how to begin, right? How do you get started? What's the first thing you should work on? And we've talked before about doing top-down programming and bottom-up programming. Top-down programming, you start with main, and then main will call into functions that don't exist yet, so you stub those out. And then after you got all of your main done, then you go to one of those stubbed out functions and write it. And when it calls functions, you stub those out. A stubbed function is like a fake phony function. If you ask it to generate a number from 1 to 100, it just generates 50 or something like that. You haven't actually written it yet. It just kind of gives you something that could be plausibly valid. You work your way down. Bottom-up programming, you do the opposite. You write all of your bottom-level functions first. Then you write the functions that call those functions. You write the functions that call those functions that call those functions until you work your way up to main. And there's different ways of approaching it. And sometimes people will mix the two and do top-down and bottom-up. And the approach I'm going to show you today is, now that you know what classes are, structs, classes are basically the same thing, how to work that into your design of a new program. And so there's no right or wrong way of doing this. Everybody's got their own approach. You eventually develop like kind of an intuition for how to do this over the years of programming that it takes. But really that ability to take a problem that's big and complicated and kind of like break it down and solve it is really what computer science is. That's the heart of computer science. That is what computer science is. Okay, so let's say I'm going to simulate billiards or pool or something like that, and I want to be able to hit the cue ball in any direction with the cue stick, and it's going to bounce around until it hits a pocket or goes to a stop. So first question, what does it take to describe a ball? And I want all of you guys on chat right now to be responding. What describes a pool ball? I don't know if you guys have not played pool. Let's see, I'm looking around to see if I have any suitable objects in here. Here you go. Here's a pool ball. It's an apple, but whatever. So what physical attributes do you have to, like if you're going to describe a pool ball to me, what things can you describe? Let's put it that way. Color. Okay. So this is red, obviously. Shape. All pool balls are going to be round. So you probably don't need to hold that in a variable. Basically, all these things you described to me, these are all going to be held in variables. And probably you don't need to describe a pool ball in a variable, but maybe. I don't know. So let's do this. So we're going to describe a ball, right? And so what do we have here? Color. So color is RGB, right? And so you'd even make our own struct for that. So struct for color 3 could be a integer red equals 255, green equals 255, blue equals 255. So we'll default to white. Okay. So every ball could have a color 3 called color, and so that'll default to white on the ball. It's a cue ball by default. And then we've got rolling resistance, friction, sure. I'm not going to implement that, but sure, we can put that down, like double like friction or something like that. Heavy, so it's mass. So you have double mass, and we can have it default to, I don't know, 1 or something. Sure, mass will matter if we have it colliding with things and stuff like that. The color, the shape, the low friction. What else? What else describes a ball on a table? Strapper is solid. Good. So we could have it be number. Yeah. And we'll default to the 8 ball or something. I don't know. Size, sure. Double size. I'll default to 1 unit. I don't know. I don't know what units we're talking about here. It's the size of the centimeters. Billiard balls, drawings, and dimensions. Oh, okay. There are different sizes. All right. American. Okay. So this is going to be in centimeters, and so 5.715 centimeters. Or 2¼ inches. What is the weight? What is the weight? Let's see if we can. 160 to 170 grams. Okay. Neat. All right. So double mass, we'll do 165 grams. Cool. All right. How shiny it is? Yeah. So we need something for like the material on it. We're not gonna. We're doing text, right? So shiny. For what we're doing today, we don't need that. What do we need to describe, to draw the thing on the screen? Like I was drawing a dragon to do the Dragon Ball joke earlier. What should that be held as? What do you guys think? Character, yeah. Although a dragon is a Unicode character, which is a string, not a character. So we will need a string for the, what do you want to call it? Print the icon, maybe. Sure, I don't know. And it can default to a, I don't know, what do you guys feel like? Cat, maybe? Why not? It can default to a cat. We can have background color, we can have foreground color. I don't know if you guys saw that, but like you see how the thing has like the, I wanted kind of orange because it was supposed to be a Dragon Ball, you know? It should have had like a red, because I don't know if you guys have seen what a Dragon Ball looks like. They're kind of orange with like red stars on them, kind of. But they wanted cerulean blue, so we did that. Okay. So we can have a color and a background color. We can have the number that it is. We're playing pool. Probably not going to use that, so I'm going to all the things commented out are all great ideas that I would do if I was making a real pool game. But I'm not going to do it for now. I'm doing a stripped down version of pool. The ramen character. Okay, what else? There's two very important things that we need here that describe a ball on the table that we're not tracking yet. Position's one of them. Moving or not moving. True or false? True, it's moving. False, it's Boolean. Boolean velocity, like that. Is that... If it's on the table or not, sure. Sure, we can do that on the table, you know. If you knock it off the table, you do PvP pool, right? We were joking about that in the previous class. If you take out the other player 3 times, you get a TKO victory. If it's on the table, I don't think we're going to track that. We'll just, you know, have it always on the table. But beyond, okay, so position, yes. And so for this, we're going to do a vector 2. And we're going to do a double x equals 0 and a double y equals 0. In reality, if I was making a video game, it would have x, y, and z. For this, since we're just drawing it on the screen, which is 2D, we're going to do a 2D pool simulator. So it's going to have a vec2 for the position, but then what should the velocity be? So I was joking about it being a Boolean. What should the velocity be? What type should velocity be? A single double? Double velocity? Does that make any sense? It could be speed, not velocity. What do you guys know the difference between speed and velocity? Velocity is speed and direction together. So we can do both position and velocity as a vector 2. So velocity, you can have an x and y. You can go in the x direction, you can go in the y direction, you can go in a combination. So velocity is a combination of speed and direction. And you can hold that as just an x and y value. The x is how fast it's moving per second. Velocity is units per second, whatever the units are. I don't know. Centimeters per second, let's say. I don't know. Probably not going to use size either, to be honest. Whatever our unit is, that's how many units per second it's moving. Okay, so yeah, so velocity has an x component and a y component. How fast it's moving in the x direction could be positive, could be negative. How fast it's moving in the y direction could be positive, could be negative. Okay, so what else? What else describes a ball? No, not obvious enough. Yeah, it's got a rotation. So every ball has not only a rotation, but it also has a angular velocity as well. And I'm not going to do it. Okay. So, but again, it's the kind of thing that you would simulate if you're making a 3D pool game, right? Because you want the balls to roll. And so they're going to not only have a rotation they're currently pointing in, so to speak, but they change over time as they roll down the pool table. Okay. Is it bouncy? Yeah, sure. That's another thing I'm not going to implement. But you could have like what's it called in physics? Like the elasticity or something like that. Yeah, we're not doing that. Okay. But I like it. I like what you're thinking. Elasticity 1. I don't know. Is it bouncing? Okay. Yeah. So when they collide with things, are you going to get an elastic collision or an inelastic collision? There's a lot of questions you can put in here. I think that's pretty good for now. I don't think we need mass either. Color background, color icon, position velocity. That's pretty good, I think. All the things commented out there are all great ideas from you guys, and we can put those on our to-do list to do later, i.e. never. So let's describe the ball. We just did the ball. Let's describe the table. So what sort of state do you have to maintain for the pool table? What information describes a pool table? If you've never seen a pool table, I will pull one up here. Is it level? All right, there's a pool table. So if we're going to be doing a 3D game where you're playing pool, there's a lot of things that I can think of to describe it. You know, if you were going to describe it to me, like how would you describe this table to me? You know, how's this one different? How's that one different? Okay, that just seems like a bad idea. I don't know. I mean, it's cool, but that just seems like a terrible, terrible idea. That's a fancy one. All right, so what's different with all these tables? I'm just gonna leave this horrible nightmare up. Okay, it's a rectangle with holes. Okay, yeah, I mean that's the important thing, right? Like it's the pockets, right? And felt table, 6 holes for the balls. How big is it? Of course, now that I've decided to do this in metric, there we go. All right, let's just go with this one, whatever it is. Regulation size is 50 inches. Give me the metric. Standard pool table. All right. Not useful. Oversized 92 inches by 46 inches. Pro size, regulation size 100 by 50. Okay. Pool table size and metric. There we go. Okay, 284 by 175. All right, neat. So we're gonna describe a table now. Yep. And so we can have things like size, you know, double size in the x direction is equal to 284. Size in the y direction is equal to 157. Regulation size 9-foot table. Number of legs 6. What else? What else describes a table? If you're going to describe a pool table to me, what else would you say to me? The weight? Maybe. The edges? The borders? The texture? Yeah, okay. So, the shape. Yeah, so we might have something like a model, you know, like a 3D model of some sort. I don't know. Maybe something like that, right? Where you have a static mesh for the model. But it's not really, doesn't really matter for what we're doing right here. Shape of it's always going to be rectangular, I think. We don't. It's kind of like with a ball. Like you kind of don't need to store the ball's sphere, you know, because all the balls are going to be balls. I think, you know. Pool table hopefully should be level, and it hopefully should be rectangular. That's something that's not the case. You're playing pool on the Titanic, then, you know, you can add that later maybe. Location of the pockets is a good one, yeah. So you can have a vector of vec2s called pockets. And we can put all of the locations of the pockets in here. So the size would be, make this a const static. That work? No, it has to be static. Don't worry about that. Makes it a constant. The table can't change size now. Okay, and so let's maybe sketch this out. And this is a lot of what I do, like when I'm beginning a piece of software, like I'll actually like kind of sketch this out and like think about like where the pockets on a pool table are, you know? So if this is 0, 0, and then what we say our dimensions were 284 by 157. Okay, so this is like 283 by 156. Down here, then what are the locations of the 6 pockets? This one's going to be at 0 to the right and 156 down. What is that location there? What is that location there? Give it to me in the x and y coordinates. Okay, this is x, this is y. I'll start typing them in here while you guys are coming up with the other ones. So we got one at 0, 0. We got one at 0. $156. We got one at size x. Okay, so here are the 3 that I've given you: 0, 0, 0, 156, and 0, or 283 by 156. Yep. 142, 0, so that's, yeah, sure, good enough. 141, technically. So 283, or 284 divided by 2 is 142. So 142, comma, 156 for this one. 142, comma, 0 for this one. And then what is this guy here? Good, Fernando. It is 283, comma, 0. Yep. So we can add all these pocket locations to here. And so split screen this maybe. Oh, no. Okay. So now we're going to add size x divided by 2, 0. That's this guy up here. And then we're going to add size x divided by 2, comma, that one. Size minus 1. That should be 1, yeah, 156. Okay, and then for this guy, that is going to be size x minus 1, 0. Okay. Cool. So now we got the location of all the different pockets, and we should probably have something for like the size of the pocket. What do you guys think? Like if the ball comes within yay big of the pocket. And we can look this up. How big is a pocket in pool? How big are pockets anyway? Multiple articles on this. Okay. Okay, that's not helpful. Yeah, it's great that you tell me their standard sizes and then not give it to me, right? Recommended. Okay, here we go. Let's go here. Pocket liners, pocket openings, and measurements. Here we go. Rubber faced minimum, maximum, thick may be used. Pocket jaws. Okay, that's the. Okay, here we go. The corner pocket mouth is 11 centimeters. Side pocket mouth is 12 to 13. Okay, so they're actually different. But I'll just put down 12 and we just keep them the same. Right. If you're wondering what static constant square means here, it just allows us to set a constant inside of a class. There's a reason for it, but it doesn't really matter right now. Okay. Wouldn't it be within 1 unit of the pocket? Yeah, well, if it gets within 12 units, let's say. So if it gets to like centimeter 1212, then it falls in. I guess our units are going to be centimeters per second. Why can't you use a const double? Has to be constant square. So doubles and floats are weird, and you'll learn why in 4th semester computer science. So for now, just be aware that if you do an int, you can do this. That's fine. But for a double, you have to do a constant square. Okay. It's the same thing. It's a constant. Don't worry about it. It's determined at compile time. So you've got a size X and a size Y. They're fixed at compile time. They can't change. Static just means it's associated with the class itself rather than each individual object. So you don't have to make extra, like if you were to make like table Bob and table Sydney, if they were just regular variables like that, then you'd be making 2 variables for each of them. And so if you're making a lot of tables, then you're going to waste memory when there's absolutely no reason to. Like it shouldn't really take up any memory at all, really. They're just fixed constants, and so they don't have to take up any RAM. We can do it this way. But if you didn't know about this, you just make them a variable, and it would be fine. It's not a big deal. Okay, good question. 6 legs. We could probably make this a static const. Also, because we're fixing it for the regulation, 9-foot regulation tables have 6 legs. Okay. So, maybe in the future, if we want to support different kinds of sizes of tables and different variations of tables, we could do so, but this is fine. Okay. What else were we talking about? We're talking about the felt. So like the friction, there'd be like a coefficient of friction on the thing. So this would be like a double coefficient of friction, which we looked this up in the previous class, is 0.22. I'm also not going to use it. So that's going to go up there in the code graveyard. Maybe we'll get to it someday, and that day will never come. But yeah, we actually looked it up. That's the coefficient of friction on a felt table, I believe. So if we wanted to have the balls slow down as they play. Okay. So got the size of the table, legs of the table, pockets. The actual appearance would be held in this variable we're not using because we are in text land. Okay, so now we could figure out like a draw function or something, right? So we haven't learned member functions yet, so actually before we get going, does anyone want to know more about this vector 2 here? Like, do you understand what this is, what it's doing, what you do with it? Everyone kind of give me a thumbs up or a thumbs down. Do you understand this? Yes or no? Give it to me on chat. It holds the position of something. Yeah, it's X and Y location. Okay. Let me show you then. Before we go on to this more advanced stuff, let's just start with the basics then. We've got here a struct called vector2, and it's got inside of it an X and Y variable. So let's do this. So let's go here and say vector2 mua is equal to 10.1 and 20.2, and we see out mua.x. Nathan, what is this going to print to the screen? Let's say we're using this variable to track your location in the world, your latitude and longitude. So Nathan, what is this going to print to the screen? Nathan, you here? Yes, what this is doing, this code here is the same thing as if we had made a vector2. The variable is named mua, and we're saying mua.x is equal to 10.1, and mua.y is equal to 20.2. So this is a new variable type called vector2. We made this new variable type up here, and now that allows us to make vectors, or vector2s, variables of that type, vector2. And so I made a variable named mua, who's of type vector2. So that means that mua has two subvariables. The two subvariables are known as x and known as y. And they default to 0 if you don't give them a value. So if I were to print out mua.x here, everybody, what will this print? What do you guys think? All of you are wrong. Okay? It will print 0. We'll print 0 because I'm no longer initializing the value to 10.1. When I do this, it will use the default values for x and y, which are, again, 0. So when we print it here, it's going to print 0 to the screen. Okay? Not 0, 0, just 0. Okay. Then we're setting mua's x to be 10.1. We're setting mua's y to be 20.2. And we're going to print out mua's x. So Nathan, what value is it going to print now? It's tracking your x and your y location. We set your x location to be 10.1. Your y location to be 20.2. And then we want to print out your x location. So what is this going to print to the screen? 10.1 is correct. Good. So now let's, we can run it, I guess. So we get 0 and then 2.1. Cool. Now, what if we do a color? So Ryan, what is your favorite color? I'm going to make a color 3 called Ryan. Blue. Okay, 00255. So a color 3 is a new variable type that we just made up out of the blue, out of our imagination. And every color 3 is going to have 3 subvariables. One named red, or R, one named G, one named B, or blue. Okay. So we can initialize this to red 0, green 0, blue 255. And so if we were to, for example, see out Ryan.B, Ryan, what value is this going to print to the screen? .255 is correct. Yeah. Because this code here is the same thing as saying Ryan.red equals 0, Ryan.green equals 0, Ryan.blue equals 255. This is something called universal initialization syntax. And it allows you to initialize all the member variables in a struct in the order that they're declared. So red was first, green was second, blue was third. So that one's red, that one's green, that one's blue. The order they're declared is the order you initialize them using universal initialization syntax. So It's a lot more compact than having to do this, right? Okay, so that's going to print 255. Now let's say that we want to print Mua's location. In the color that Ryan picked, right? So there's his location, latitude and longitude. How can we change the color of the font to blue? As it turns out, there is no way in the standard for doing that. But I have, however, made a header file that makes that easy peasy. So it's called colors.h. You can find it on GitHub. And you can do this now. So you can say set color to be Ryan.red, Ryan.green, Ryan.blue, like that. And then we can reset the color afterwards so we don't leave the font permanently blue. We can do that. And now it's going to print out the location of Mua in blue. Okay. So somebody else give me their favorite color. Anyway. Green, yellow. All right, these are like boring colors. We're going to do taupe. You guys know what taupe is? If I could spell it right. Thank you. Taupe. Taupe? Taupe? How about mauve taupe? Anyone know what color mauve is? Mauve taupe. Okay, so when you get colors, oftentimes you will get them as a triad, 3 numbers, red, green, blue. So 57 red, 37 green, 43 blue. So I can just punch those in over here, right? 53, blah, 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 blah. Or another thing that's very common is you get it in a hex code like this. So the first 2 digits are the red, the next 2 digits are the blue, and the last, red, green, blue. Sorry, the first 2 are red, then green, then blue. Okay. And so that will give you mauve taupe. All right. And so I can enter this any way that I want. So I can make it named mauve taupe. And I can enter it like I had there, 57, 37, 43. I can do it like that. That's fine. Or I can actually enter hex codes like this. So what was it? 91, 5F, and 6D. And these can be lowercase letters, they can be uppercase letters, it doesn't make the slightest difference. So this is called hexadecimal, and it is a more compact way of writing things like color information and things like that. These are 3-digit long numbers, the red, green, blue, so you can use 9 digits to hold the color. With hex, you only need 6 to represent any of the standard color space, RGB color space, 8-bit color space. Okay. So you can see it as hex, you can see it in RGB, you can see it in float, et cetera, et cetera. So this works fine. And so the 0x you see there is not 0 times. It actually means the number that follows is a hexadecimal number. Okay. And so I'm entering hexadecimal 91, hexadecimal 5F, hexadecimal 6D. And so I can either just use normal decimal numbers or I can use hex. Either way, whatever makes you happy. This will make you look cooler though, I think. And so we can set the foreground color to Ryan blue. We can set the background color. That's also a function in my library. We can set it to mauve taupe, like that. And dot. There we go. So now when we print out the that is not a great color combination. I'm sorry. Mauve taupe and bright blue are gangrenous together. So somebody suggests me a color that will look better with mauve taupe. In the previous class, a subtle shade of blue, 50 Shades of Blue. In the previous class, somebody suggested flamingo pink. And so flamingo pink is you. FC8E. So sorry, Ryan is being deleted. Color 3, flamingo pink. It's going to be equal to 99, FC. Again, it doesn't matter if they're capital or not. 8E and AC. Also known as, that's where I got it from. Also known as 99, 56, 67. Same thing. It's just a different way of representing the same bits. Okay. And so Ryan, 4S, going to turn into flamingo pink. Oops, missed. There you go. And that, I think, goes together a lot better. The mauve taupe and the flamingo pink complement each other, I think, a lot better than the blue. Would you have to type out the RGB every time for the color? No. If I was fancy, I would have a my function itself would take a color 3, right, and then you just pass a color to it. But the function itself requires 3 parameters, so I'm having to pull out the red, the green, the blue. Realistically, I could just make a color 3 class and have it take that instead. Make life a little easier. All right. Okay. So thumbs up, thumbs down. You guys understand the vector2 class now? Whenever you make a variable of type vector2, you get a .x, you get a .y. And then every time you make a color 3, you get a red, a green, a blue, and a hex. Don't worry about hex. But it's just a different way. It's a whole lecture, but you go into programmer mode, you type in 90. 90 is 5A in hexadecimal, and it's 0101, 0101, 1010 in binary. So there's just different ways of writing the same number. They're all the same number. They're all 90 in decimal. But there's just different ways. You write an octal as 132, and hex is 5A. Hex is just a little bit more compact. It allows you to write the same information, but instead of 01011010, you just write it as, 2 digits instead. So, all right. So that's pretty cool. Now we're going to need to actually do our billiards game. Yeah. So, code graveyard time. We're going to make a ball. And what should we name our ball? What's the favorite name for... Somebody give me the name of a ball. The first ball. Okay. Ball number 1. How about that? Okay. Now, where should it start? Where should it start on the table? Football, left shark. We'll just say it's the number 1 ball. Okay, where should it start on the table? Where do you guys want it to start on the table? The table, remember, is 284 to 157. Okay. Where should we start it on the table? What do you guys think? Just pick something. Not off the table, just somewhere on the table. Somewhere between 0, and 284, 157. You want it on the left side, in the middle. You want it just in the center. Where do you guys want it? 0. And right now it's at 0, so we just leave it there. It's fine. Olson wants it at 0 in the x direction. And we need a table too. All right, table. And table dot size y divided by 2, something like that. So it's going to start on the left edge, halfway down, something like that. 86, 128. Okay. Size x to the third. So okay, yeah. Okay, all right. I like that. All right, I like that one. Table dot size x divided by third. So it's going to start a third of the way over, right? And halfway down. So starting position in pool. No, raw. No, not the right pool. Why? All right, that's not. Yeah, like that, right? Like you start like kind of like a third of the way in. Thank you, my goodness. Okay. All right, so yeah, that's good. It'll start a third of the way in the middle. All right, I like that. I like that. Okay. All right. What else do we have on the ball? The icon, it's going to default to a happy cat. What color should the ball be? Don't give me like red or blue. Give me something exotic, like mauve taupe or pink flamingo, like cerulean blue, burnt ochre, or whatever that crap was. Crayon, burnt ochre. Am I just misremembering this? Raw umber, raw sienna. Burnt, okay, there is a burnt ochre. There we go. All right. No idea what that means. Why would you burn ochre? I don't. Robin's egg blue. There's burnt orange, burnt sienna, burnt umber. Okay. Cocoa. All right. Oops. Hex code. Okay. I like it. Full red. Okay. All right. So do you want this the background color of the ball or the foreground color of the ball? Background color. All right. So this one was 255 220. All right. And then royal purple. All right. Royal purple. That's good. All right. I don't know if this is going to complement the bright red that we got there, but why not? And this one is, I'll just do an RGB. 47, 32, 66. All right. And you guys, what icon do you want for the ball as it bounces around? The previous class has already taken the dragon ball idea, so no dragon. Something round. Okay. All right, so one dot icon. Round. Lollipop. That's okay. Potato. How about this one? Should we use? You cannot put a GIF into it. No, unfortunately. Let's see. Actually, an egg would work pretty well. Yeah. Or maybe, let's see. Circle. Hollow red circle. Purple circle. Yellow circle. Orange circle. Red circle. Yeah, let's see the circle that has eyes on it. I like that. That's very similar to the walnut from Plants vs. Zombies. All right. The wheel's pretty good though too. Okay. All right, so we got our icon now. Now we need to actually do the game. All right. So we need two different things. We need the ability to draw the table on the screen, and we need the ability to draw the ball on the screen at the location the ball is. So the table is supposed to be yay big, and we're going to need to scale it down to the size of our screen. Okay. So is there a function that tells us how big our screen is in terms of characters? get terminal size is what it's called. I could not remember. All right, so then see, so there's a function called get terminal size, and this guy is going to return a pair. Thank you. Autocomplete, very cool. All right, so this is going to return a pair of integers named row column, and this is going to return which one's first? Rows first, then columns. Oh yeah, we can do that actually. That's C++ 17, but it's kind of cool. Anyway, so this is going to make two variables, one named rows, one named columns. So it's actually splitting the pair into two different variables. And so we just see out rows and columns. And so you can see that our terminal here is 32 rows high and it's 118 rows long. So we are going to need to scale the table down. What do you guys think? So if you just divide it, I guess, right? Like, okay. Yeah, get the ratio between the sides, right? Yeah. Okay, so we just output like table.x size x by columns. Trouble is it's not going to be uniform scaling, I don't think. So yeah, it's gonna be scaled really weirdly. So maybe if we want to keep it proportionate, we should scale the whole thing down by like 5, basically. You know what I mean? Because the table's supposed to be like this tall and the screen's only 30 columns high. And it's supposed to be this wide. And so it's like the table is 2.4 times wider in centimeters than we have spots on the screen, but the table's 5 times taller than we have rows on the screen. So we could just divide the whole thing by like 5, I guess. Yeah, that'll work. All right. All right. Let's make a function called void draw table. And it's going to take in a const table by reference called table. And it's going to take in a double called the scale factor, which we're going to set equal to 5 just for the heck of it. And so we need to draw the edges of the table on the screen. What characters should we use to draw the edges of the table? In the previous class I used asterisks, but you can suggest anything you want. So we're going to say for every row, for every column, if for every row, for every column, if we are on the edge, we're going to draw the character, the ramen character. That would probably screw it up though. Because Unicode works really weirdly when you output multiple ones. Like it doesn't line up properly. Yeah, it's true. If we're on the top edge, okay, yeah, sure. All right. Horizontal character is going to be the hyphen, and vertical const char. Vertical is going to be equal to the vertical slash, something like that, maybe. So then what about when we're on a corner? Front slash, backslash. Not worry about it. Okay. Ninja Cat. Okay. So basically, yeah, we can do something like this, right? We say for int I equals 0, I is less than table dot rows, which is its y size, plus plus. So for every row, if we are on the top row or the bottom row, no, that's not right. We can do this. Const rows is equal to table dot size y. This is how many centimeters tall it is, right? but we have to remember we're going to scale it divided by scale. That'll be an integer. Okay. So we're going to scale it to how many rows on the screen. So the table in real life is 157 centimeters. We have 30 rows on the screen, so we have to divide 157 by 5 to get the row on the screen we actually are. Okay. So, and then columns is going to be table size x divided by scale. Okay. For every row. Okay. So for every row, if we're on the top row, if we're on the bottom row, then we do the whole horizontal. If we're on any of the middle, you guys understand what I'm saying? Like, if we're on the top row, if we're on the bottom row, we draw all of the characters, and then if we're on the left side or the right side, we only draw it on the left and right spot. Okay. So we're on the top row. Okay, so if I is 0, or I is equal to rows minus 1, top row or the bottom row, then for int j equals 0, j is less than columns, j is less than columns, j plus plus, see out the horizontal character. And see out the other one. Okay. All right. And then, so the top row, the bottom row, we draw all the horizontal lines, we go to the next. Okay. And then after that, then we're just going to say, otherwise, is there a function to move the cursor on the screen? Yes, there is. Okay, so row I, column 0. Otherwise, we're just going to print the vertical character and then move the cursor to I to the right edge of the screen. My Lord, killing me here. Autocomplete. And then print it out again. So we're going to print out the vertical slash on the left side, then we move the cursor to the right side, print that out, then we go to the next row also. And that should be good. I don't think we even need the end line at all. We're doing this. Just maybe at the very end, we'll do a scout out flush, just like an end line. Let's try that. Let's see how that works. A lot of hypotheticals going on here. Draw table, passing in table, passing in 5. Okay, there we go. Got a table. Like an off by 1 error, it looks like. And yeah, see that right there. We do need a scale down a little bit more. It's drawing the vertical slashes on the first row, which it shouldn't do. So on the first row, if the row is 0 or it's the bottom row, then it should do all the horizontal lines. Otherwise, it draws the vertical lines. It should never draw the vertical lines on the first row. Well. me do something stupid. All right. There we go. All right. Everything's fine. Everything's wonderful. All right. So we are currently drawing the table. And I guess we don't need those numbers in there anymore. So we can properly draw the table. So now all we need to do is simulate the bouncing ball. Okay. So let's just do a function call for that called simulate ball. And we will pass in the ball. And this will be an infinite loop, maybe? I don't know. Yeah, whatever. Const ball by reference. Ball. So, yeah. So basically, this thing here tells the compiler, yeah, by the way, I know this thing's not ever going to return. Don't worry about it. All right. So we're going to go into infinite loop. And then what we're going to do is we're going to draw the ball on the screen. We're going to pause for a fraction of a second. Then we're going to clear that spot and draw the ball on another spot on the screen. Okay? So, what velocity should the ball have? Also, that's a good question. We've got its position. We don't have its velocity. What do you guys think? Probably have to make this scale shared among them. Five tilde and dot, and there we go. Okay. Well, the velocity 2 should be able to traverse the entire table in 5 seconds. Okay, so you want to just bouncing left and right to begin with. The table is 284, so it should have a speed of 284 divided by 5. So it'll have a speed of 56.8 and a vertical velocity of 0. Okay, so now we just need to simulate the ball. Okay, so what we're going to do is we will do the physics. All right, so ball.position.x. So how do we move it? What's the physics? What does velocity do to position? How do we? What do we do here? The motion, okay. So the velocity is in centimeters per second. Well, how long has it been since the last frame? What's our frame rate? I don't know. Maybe we should figure that out. Const frames per second, 30, 60, 100. 120? 30? I don't know. 120? Sure. Get that buttery smooth animation going on. All right, so if that means we're redrawing the screen every 120, let's just do 100. Let's make math easy. Okay, so the position of x is going to be increased by the ball's velocity, x velocity, times what? Position equals velocity times starting position, anyone? Times time. Okay. How long has it been since the last frame? Well, 1 over the frame rate. Okay. So it's been 100th of a second since the last frame, assuming we're not doing anything else that takes a large amount of time, which we're not. Right. So at 100 frames a second, it'll be 100th of a second since the last frame. So every frame, we are going to move the velocity times time. So if your velocity is a meter per second, and you have 100 frames a second, you move a 100th of a centimeter, 100th of a meter a second. You guys understand that? So if our velocity is, what is it? 50. Okay, so our velocity is 6. If we are updating 100 times per second, then the delta t is what that is. It shouldn't be t, it's delta t, is equal to 1/100th of a second, right? And so if we're moving 58 centimeters per second, then every quanta of time, we're going to move 56.8 divided by 100. In other words, we're going to move 0.568 east every frame. Okay. So we can adjust our frame rate up or our frame rate down. It won't break physics at all. I'm looking at you, Elden Ring. A lot of games have the frame rate hard-coded into the engine, and that's really bad. Yeah, normally you would figure this out from like you would have a time function. You would check the current time. You'd see how long it was since the last time, and that's your delta t. We're just gonna, do this instead. Okay, and then we will do. What are you mad at? Oh, it's a ball. Okay, fine. It's a constant. I mean, it's fine. The ball will change. So its x position will increase. The higher the velocity is, the faster its x position will increase. Its y position is not going to change at all because our y velocity is 0. Okay, so let's draw it on the screen. So this is the physics. And we'll have a little to-do here. Bounce off the edges, right? And to do this, we'll probably need the table passed in as well here. Table reference table. The simulate function is going to need to know where the edges are for it to bounce. For now, we're just going to see if this works. Okay, so every frame, we're going to move the ball based on its velocity, and then we are going to draw it on the screen. So we are going to use move cursor, and we're going to take the ball dot position dot x divided by scale. Because remember, we're translating units from centimeters into text positions on the screen. So we have 30 rows, and so if we're dividing by 6, then 180 centimeters turns into row 30. That's what we're doing with that ball, and that's it's actually rows first. It's not x, not s. We're going to move the cursor. There might be an off by 1 error there as well. And then we will see out ball.icon. do cout dot flush. So it appears on the screen. And then now what? Because we're immediately going to go into the next. We're immediately going to go into the next frame. Any of you know what the function is to go to sleep in class? It's my student's favorite function, to go to sleep. What is the function to go to sleep? There is, in fact, a function called sleep. But it is seconds, and we don't want seconds. We want microseconds. So what is the SI prefix for a micro? Anyone know? The mu character. So in Unix, it is called usleep or microsleep. Okay, that looks similar to the mu character. So usleep is a very useful function for students to know. In case class is just too boring, you can go to sleep, and we're going to go to sleep for delta t seconds. So after we do this, we sleep for 1/100th of a second, and we're kind of assuming that all this takes effectively 0 amount of time to do. May very well. And so we're going to go to sleep for 1/100th of a second. And then we're going to wake up again. We're going to draw the ball again. We're not clearing the ball currently, but let's see what this does. Okay. Structure binding set, but not used. We don't need you anymore. We've already gotten it. Okay. All right. What's going on here? Let's see out ball dot position dot x and ball dot position dot y. Yeah. So you see the horizontal position is in fact moving. The vertical position is not moving. The trouble is it is divided by 6, and so it is flying off the edge of the map. So it has already exceeded the right edge of the screen. Should probably just add bouncing at this point. I don't know. Or we just make the velocity slower. Let's make the velocity 1. So it should move 1 centimeter east per second. And you can see it's not. It's actually traveling faster than 1 centimeter per second. Or maybe it's just updating really fast. Did I not do the usleep? Oh, that's why. All right. So this is in seconds. Delta t is 1/100th of a second. We need to multiply this by how many microseconds are in a second. And now we're moving at a leisurely 1 centimeter per second. Yep. So usleep sleeps for delta t microseconds. Yeah, that's why it wasn't sleeping at all. It was just updating so fast. All right, now do you guys see the approach towards debugging? You have to see out all of the things, right? And just see what's happening, right? In professional practice, you would log it instead of seeing out it to the screen, but that works. And then back in here, you can see the ball is going to very slowly moving 1 centimeter a second on a table that's, like 200 centimeters wide, right? So it's working. Now, it would be cool if we could turn off the cursor, right? Just waiting for autocomplete. There you go. Thank you. Set cursor mode to be false. Okay. Turn off the cursor. And there we go. All that's working, so we can put the velocity back up again. And you can see the ball is now very happily on its way to go kill the opposing player. So, it just saved the border, because we're not redrawing the table at all, right? In order to cut down on flickering, you want to actually cut down on how many times you clear the screen and redraw it. We could clear the screen. There's a function called clear screen. We could redraw it every time, 100 times a second, but you're going to start seeing flickering as you clear and redraw over and over again. And it's, in a simulation like this, it's actually better to just erase the old one and draw the new one. Okay, so all right. So we want to cursor is still there. Okay, so we are going to see out that, because the cursor should be set. If not, we'll do that. Okay. Okay, and then we can give it like a vertical velocity as well. Right, so it's going downwards because positive y is this way, right? And you can see it's very happily traveling off into La La Land. It's making a break for it. Okay, so we are, so sleep wouldn't work, because sleep takes seconds, but it takes a whole number. It doesn't take a double. So you can't do half a second. If you want half a second, you have to use microsleep. All right. So what do we do now? What's the next thing we should implement? We got 30 minutes left in class. What should we do? Okay, so how do we know when it hits the border of the table? How do we get that? When the position of both is the same. Well, remember the table has four, it's got four edges, so to speak. So when the position is equal to row minus 1. But I mean, where's that? We don't actually have that's in a different function, right? This guy up here, where we computed our rows and our columns, that's in a different function. We don't have access to that. We're down here in simulate ball. So how can we tell if the position of the ball is outside the rectangle defined by the table? We do have the table, by the way. We do have the table. How do I get the size of the table? How do I get the X size of the table, let's say? Yes, that is correct. So if ball.position.x, well, the top left corner of the screen is 0, right? So if it's less than or equal to 0, then we're off the left side of the screen. Then we're going to clamp the position. The ball's X position is now 0, so we don't draw it off the edge of the screen. So if we hit the left edge, we just stop at the left edge. And then what do we do with the velocity? So if we're traveling left, which looks right, okay, on the video. Okay, here we go. You're traveling left and you hit the left edge of the screen right here. Which way should the velocity be going now? What do we do with the velocity when we hit the edge of the screen? We go one way. Right, what do we do? Reverse it. Make it negative, okay? So we say ball.velocity.x times equals -1. So you put your thing down, flip it, and reverse it. It's a Missy Elliott line. You wouldn't get it. Okay, so what's our issue here? Number name vector velocity. How about now? Okay, good. All right. So if our velocity was 5 and we hit one edge, then our velocity is now -5 going the other way. When we hit the other edge, our velocity is now 5. We go here, velocity is now -5. Should we add in elastic collisions and things like that? Yeah, sure, probably, but not now. Okay, so that's the left edge of the screen. Now we have to handle the right edge, right? So how do I get the right edge of the screen? What did I put down here? How do I know what the right edge of the table is? Table dot what? How many centimeters wide is the table? It's on the screen. Now, position and velocity are both held in centimeters. The scale is only used for drawing it to the screen, right? The scale is only used to go from centimeters in the world to which row and which column are on the screen. But all of the physics simulations are all done in centimeters. So table size dot x minus 1, sure. How about that? And then that table dot size x. Pull it in a little bit, maybe. Back it off a centimeter from the edge. Makes sense. Maybe we could use the radius of the ball there. You know, remember we wrote down the ball has a diameter of 5 something centimeters, right? Maybe we could actually use that there. A little more realistic. Make it more realistic. I don't know. No. not for today. Okay, so if we hit the right edge, we flip. If we hit the left edge, we flip. And that's pretty good. Now we're just going to do the same for y. And to do bounce off edges can go away now. Okay. ry dot 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 table size y, table size y. Maybe we should back it off a little bit more. It's rounding into the row and column, right? It's the slime that we're drawing here is just nomming the border, right? Should probably pull it in a little bit. That's actually kind of interesting, huh? Not exactly the same spot every time. But it's close. Thought it was Pac-Man. It thinks it's Pac-Man. Okay. So maybe we'll pull it in a little bit. Maybe. I don't know. Tables, maybe we should make a bumper thickness or something because of the, you know what I mean? Bumper thickness. Pocket size. Oh, we don't have pockets. We need a pocket. Bumper size. Let me make those. They're probably 12 also, right? About the size of the pocket. We'll just do that. Okay, so down here, we can say table dot bumper size. Minus table dot bumper size, table dot bumper size. So we're just going to back it off about 12 centimeters. You know, so it'll bounce a little bit earlier. Maybe. See if that makes a difference. It'll still probably go into the edge. No? Okay. Yeah. Yeah. Okay. So the nice. Okay. So now we can play this with different colors. Oh, we don't have colors, right? We're not using colors at all. Okay, we need to change that for sure. All right. After the table, we need it in green, I think, right? Yeah. Okay. So let's do this. Set background color. What is the color? Xcode color of a pool table. What color is the felt? Pool table green. There we go. Is that a Pantone color? I kind of like this one. I like this one. Okay. So 10, 108, 3. Neat. All right. Perfect. Copy paste. Easy. 10, 108, 3 is in fact pool felt green. And then the foreground color, set color, brown, maybe? 80, 40, 20, Oh, right, because we didn't actually, fill in the whole thing. It's kind of cool though. I mean, yeah, I like it. There we go. Full screen's green now. I did a clear screen. Just need sound effects. But this is putty, so there's no sound effects. You just have to make the sound yourself. All right, yeah, you could. You could actually do snake or something like that, like this. Sure. All right. And then for the ball, we want to use the balls. Okay, so move cursor there. I think these should be probably on the table itself. So static const, they're actually static color 3, BG color for the, so we're going to have like a background color for the table and a foreground color for the table. Okay. So we've got that, and now down here, we can just say table.red, table.green, table.blue. Again, this would be easier if we had an actual color function that would table.bg color.r. Okay, so that's the more proper way of doing it. It's almost too hard to read at this point, but we're like we can set different tables can have different colors on them and things like that. And this also allows us down. We y2y this and come down to here. When we erase the ball, we can replace it with the felt color. That's why I went through this whole rigmarole, was so that we can actually erase the ball and put green back in its place. And then the ball itself, when we draw the ball down here, we can set the color of the ball. So was that 5S ball? So we can set the ball's background color and the ball's foreground color like that. And now it's leaking a little bit. Interesting. Oh, floating point errors, I think we're looking at here. It's interesting. It's supposed to be erasing the previous spot, but Unicode works really weird, and so you can see here it's not actually erasing the ball properly. So I guess what we could do is, instead of doing all that, we just draw the table again. And that'll clear the screen every time. We'll probably get flickering. Oh yeah, you saw a little flicker there. Yeah, but it's refreshing the screen every time, so you don't get those artifacts left on the screen. If we were doing with ASCII characters, you wouldn't have to worry about this. You can see it's smoothly updating, 100 frames a second. I can change the frame rate if I want to make it more jerky. I can make it 10 frames a second. All the math is still going to work out. So you see it's jumping a lot more here. It's updating 10 times a second. Okay. 100, 140. Let's do this. Smooth as silk. Look at that frame rate. It's amazing. Putting my 1040, putting my 4090 to good use right here. Okay. All right. So that's a full refresh here. Yeah. Okay. Because otherwise it's not erasing quite properly because Unicode's weird. All right. What else should we do? We got 10 minutes left. What should we add? Make the Centipede game now? Pockets. Good. Okay. So after we've updated the position of the... I think the pockets are actually going to be too far away now. Because the things are bumping, 12 centimeters away. I think that... I think 0, 0 is impossible to reach now. Like, it's not going to be able to hit there. So maybe we just make the pocket size bigger, and then it'll reach out and grab things a little bit further away. I don't know. Let's try it. All right. So okay. So we've just moved the ball. Now we want to see if it's pocketed. Check for pocketing. So we have to say for every pocket in the table. So we have to say for every pocket, which is a vector 2. For every pocket in table.pockets. So for every pocket in pockets. How do we check the distance between two things? What is the equation to tell the distance between two objects? In this case, the pocket and the ball. How do we do that? Standard library function to do distance, actually. Hypod it is. Very good. So it is the hypotenuse, the distance function, of the pocket's x value minus the ball's x value, and the pocket's y value minus the ball's y value. That will give us the distance between the pocket and the ball. And if the distance is less than the pocket's, the table pocket size, then the ball's dead. I don't know what to do here. What should we do if it falls in the pocket? Kill it? Exit? What should we do? Quit? Return, increase the score. Yeah, because we really want this to work with like, more than one ball, right? We're kind of doing this for one ball, right? Terminating the program every time a ball gets pocketed is probably not the right answer. Maybe we could add that to the state of a ball, right? I think somebody even mentioned this earlier. Boolean pocketed. Right. So we go to simulate the ball. If it's pocketed, just return, right? And it's not supposed to return, right? Because it's infinite loop. Yeah, sure. Okay. So we really are going to pull out that infinite loop and put it in main instead, right? Yeah. Let's just do that now. And we're going to pull out the draw table as well. So down in main, we're going to draw the table and simulate the ball. And this is going to be an infinite loop now. Okay. So we'll draw the table, then we'll draw the ball, and if we put multiple balls on the table, then we can just simulate all of them. Cool. All right. Let's see if this works before we try anything else. Bounce. Okay, cool. Neat. All right. So that was a neat refactor that worked pretty well. And cool. So if the ball's ever pocketed, it just returns and it doesn't do anything. So if we hit this, we will just say ball.pocketed is now true and just return. Something like that. I don't know. Now the question is, how do we set up the math so that it goes in a pocket? We're not drawing the pockets either. Oh, it just ended. Right. The U sleep doesn't. The U sleep should not be there. The U sleep should be here. Yes, thank you. And delta T, all that code. Yeah, we need. All of you need to be here instead, maybe. Congratulating myself too quickly. Actually, we can make these globals, I guess. Globals are generally bad, but okay if they're consts. Because they can't really affect state. You can't pass state between... You can't have one guy writing to a global and another person reading from a global. This just allows everybody to kind of be on the same page when you have a global state like that. It's not the best. It's not the worst either. Okay. Okay. All right. Cursor mode also should be pulled out. Let's see if it'll hit a pocket. Mid-center, pocketed. There we go. Boop. All right. All right, so we got 5 minutes left. How about we add multiple balls? Okay, let's do this. So, So let's have simulate ball return something there. So if the ball is pocketed, it's going to return true. If the ball is pocketed down here, it'll return true. Otherwise, it will return false. And so we can keep track of how many balls that are left, right? Something like that. So, all right. Let's make a vector of balls. We're going to start with just, notice this is actually a really important thing. Rather than immediately leaping into 10 balls, I'm going to, do you see how I did this? I made the thing work with one ball, and there were some bugs in it. We cleaned them up, we got it working with one ball, right? Now I'm going to make it work with a vector of balls, but before I do anything else, I'm going to refactor this. And for every const ball in balls, like I said, I oftentimes don't know the name of my variables until I do them, until I use them. Right. And so what I'm going to do before I add any more balls, I'm just going to see if I can, after I refactor it, if it'll still work with one ball. Okay. So rather than immediately leaping to doing 10 balls, I'm just trying it with just the one ball that I had before. But it's now saying for every ball, run the simulation on it, run the physics on it. Okay. And I'm counting how many of them are pocketed. If all of them are pocketed, the game quits. Okay, so now we can just do a couple more balls. Let's do this. We got 2 minutes. Let's get it. All right, so ball 1, and then we can do. And we can say ball 2. So give me some ideas here, people. What color should it be? Start this guy in the top left corner. It's going to move southeast. What icon should it be? What color should it be? Orange. Okay, make it a pumpkin icon. Okay, 2.icon equals pumpkin. Hello?
William available?
Yeah, could you give me a call back in like just 5 minutes?
Yeah.
All right, thank you. We're at the end of class. We need to finish this. Okay, so it's going to be a pumpkin icon. And then the color should be pumpkin colored. So 2.bg color is equal to FF 75 18. And the foreground color, I'll just make it white. It seems reasonable to me. Okay. And then we got that, and then we'll say balls dot push back 2. Now, if everything worked right, we should get second ball, which one not? I wonder if it's pocketing immediately. Let's try 50, 50. Ah, Hard-coded with 1 there. Boom. All right, ball. And for every ball and balls, simulate ball, ball. Ah, yes. Don't make that a const. And there we go. So you got the pumpkin slowly rolling southeast. See how this works? So you make sure that it works with the vector with 1 ball, and then you try adding a second ball. You're like, wait, it's not appearing. What's going on here? And then you go like, oh, I hard-coded 1. Okay, because that's what happens when you refactor. You'll forget things sometimes. And it pocketed, and we're done. There we go. Beautiful. And we just continue this process by adding as many balls as we want to the game. We just add as many balls as we want. The next thing to add, of course, would be like collision between the balls, things like that. And so in order to do that, we would probably need the simulate ball function to take in all the balls, right? And up here, const vector of balls and balls, like that. And then after we move, we could check to see if our position hits any of the other people. And if we do, then we could do something like this, where we like do some sort of physical, kind of elastic or inelastic collision, however you want to do it. You guys understand? So that would probably be the next step. And so we've got our physics going on here. We got reflections off the tables. We got pocketing working. You can see the pumpkin icon very slowly rolling down the table towards the pocket, which we're not drawing on the screen. We probably want to do that too. Probably want to put a pocket icon on the screen. But it works. So that's it for class today. I hope that was fun for you. Basically, I wanted to give you guys like an overview of like how coding from concept works. You start by having like an idea for something. You like sketch it out. Like you'll whiteboard things. You'll ask questions like, what sorts of things do I need to track? All of those things turn into member variables, and then you just code a little bit. You get that working. You code a little bit more. You get that working, and you just sit there and you just work on it and work on it and work on it. That's the system that will result in coding success. Okay, you don't want to just try doing everything at once. It's too much. Start off by just breaking off a little piece, getting it working. You saw that there were bugs in my code and things like that. Like, why is that ball not working? Maybe it was pocketing, maybe not. And if I had, if I had been mystified by it, I would have started printing out things and be like, why is this ball not appearing? And would have eventually discovered that it wasn't being called at all, right? Why is this not being called at all? Oh, it's not being called at all. So, was this bottom to top, top to bottom? We started by kind of like just getting a ball working, I guess, first. And just kind of like going from there, right? It's kind of building up. There's no, like, I'll jump around, but the main, when you're doing object-oriented programming like this, like, I'm trying to get one of the objects working. I'm trying to get balls to work, right? And having it update with physics and things like that. You add a little bit more functionality and add a little bit more functionality. And, you get the table working. Okay, that's cool. I drew the outline. I had to adjust that a little bit. It was off by 1 error. Okay, now let me put the ball on the table. And, oh, look, it's not refreshing right. Let me fix that a little bit. So that it's a little bit closer bottom to top, yeah. But in a certain sense, this is just how object-oriented programming goes. And that's a topic you'll go more into in 41. Yeah, structs and classes are the same thing, except structs are public by default. Classes are private by default. So in your Zybooks, you're going to have like a private section and a public section, and structs don't have any of that. I mean, you can add a private section if you want, but just all this stuff's public, and you're good to go. So it's easier to get into a struct than a class, because the class, you have hidden information, revealed information. It's better long run, but this is your first introduction to it. So this is how I code in CSI 40. CSI 41, you'll see the proper way of doing things, as if this is wrong. But it's fine. That's it for today, guys. Thanks, everybody. and I will see you on Friday. Make sure you guys work on Wari Part 2. Peace out.